Okay, so in this video I'm going to be going over the Topic 5 Part 3 worksheet. This is the magnetism worksheet from Topic 5.4 in your textbook. And this is a relatively short worksheet. The calculations in this unit are not super difficult. It's mostly kind of a conceptual type of unit. So let's go over some of these questions. Okay, question number 1 says, sketch in a compass needle at the labeled points surrounding the pictured bar magnet that we see over here to the right. Now, a compass needle always aligns up in the direction of the magnetic field. In fact, that's how magnetic field direction is defined. Okay, so for example, at point A, we can see that the magnetic field at point A is pointing to the right, meaning, by definition, that a compass needle would align with the magnetic field at that point, with the North Pole going in that direction. Okay, likewise, you can see the same thing would be happening at D, and the same thing would also be happening at E. Okay, so the direction of the magnetic field is the direction that a compass needle would align itself at that point. Okay, now at point B and point C, the opposite is happening, so I'm just going to rotate that compass needle around, put it at point C, and again at point B. Okay, by the way, notice that magnetic field lines, unlike electric field lines, magnetic field lines never end. Okay, they always just kind of loop on each other, so even inside the magnet itself, you still have magnetic field lines. Okay, so that would be number 1. Number 2, it says compare and contrast a magnetic dipole and an electric dipole, include a sketch of both. Okay, so this is kind of difficult for me to draw. A magnetic dipole is basically just a north pole and a south pole. Okay, so magnetic dipole, imagine a bar magnet with a north pole and a south pole. Okay, that is a magnetic dipole. An electric dipole, the equivalent of an electric dipole would be like a positive charge and an electric charge. And I'm not going to sketch the field lines for that because I can't draw that well. But these are very analogous to each other. Okay, so the one on the left is a magnetic dipole, the one on the right is an electric dipole. Now, the difference between the two is on the right, when you have a positive charge and a negative charge, you can separate those out. Okay, you can end up with what's called electric monopoles. For a magnet, you can't do that for some reason. Not that it's physically impossible, it's just that's not what seems to happen. And I say that because I want you to be very careful with how you respond to this question on the IB exam. Magnetic dipoles are not physically impossible. Okay, we've never observed one, but there are people looking for the existence of not magnetic dipoles, magnetic monopoles. We've never observed one, but there are a lot of people out there searching for their existence. Okay, because the weird thing is that there's no reason that they shouldn't exist. It's just they don't seem to for some reason. Number 3 says, explain the situations in which the magnetic force acting on a particle will have a magnitude of 0. We talked about that in a past video. Basically, if you look at the equation for magnetic force, you have magnetic force FB is equal to QVB sine theta. And so what you have here is a product of 4 different terms, Q, V, B, and sine theta. And if any one of those terms is 0, then the entire force will be 0. Okay, so I'm not going to list this out because I've already done this before, but I will just kind of verbalize it. Obviously, in situations where you have a particle with no charge, where you have a particle that's not moving, that means the velocity is 0. If you have the magnetic field, or if there is no magnetic field, there's obviously no magnetic force, so if B is 0. And then in order for sine theta to be 0, you have to have the angle either be 0 degrees or 180 degrees. Okay, so parallel or anti-parallel. Somebody asked me in a past video what I mean by anti-parallel. Anti-parallel is not perpendicular. Okay, anti-parallel just means like in the exact opposite direction, so where the angle is 180 instead of 0. Okay, so that's question number 3. Question number 4 says the current is traveling from right to left in the wire pictured here. using dots and X's, sketching the magnetic field surrounding the wire. What happens to the field when the current is turned off? Well, the last question is easy to answer. There is no magnetic field when the current is turned off. Moving charge is what gives rise to magnetic fields. And so when you turn the current in the wire off, the magnetic field goes away. Now, to use dots and X's to sketch in the magnetic field surrounding the wire, this is where right-hand rule number 2 comes in. So if it's going from right to left, the current is going from right to left, you hold your right hand out, you put your thumb in the direction of the current, that is, pointing to the left, and then your fingers, if you imagine grabbing a wire, on the top of the wires, your fingers are going away from you, and if you keep wrapping your hand around the wire, eventually they'll come out towards you on the other side of the wire, on the bottom of the wire. And so what that would mean is on top of the wire, the field lines would be going into the page like so. And they would be coming out of the page below the wire. And so the dots represent out of the page. However, as you go farther from the wire, I'm trying to draw this carefully. I'm not very good at drawing, obviously. As you get farther from the wire, the strength of the magnetic field decreases. Okay, and so what I'm trying to represent here is closer to the wire, the field lines are closer together, and as you get farther from the wire, they start to become more spaced out. Okay, so just like, as you get farther from the charge, the electric field decreases. It's the same thing when you get farther from a wire, the magnetic field decreases, although not quite in the same mathematical way, but in a similar way. Okay, question 5 is basically the exact opposite of question 4. Magnetic field created by a current in a straight wire surrounds the wire shown. State the direction of the current and explain how the right-hand rule works. Well, that picture basically looks like the one we just drew, so the current here must also be going from right to left, so the current there would be going, to the left. Okay, so pause it there before I erase this. Okay, question 6. It says a straight wire is located in an external magnetic field as shown to the right. If a current is directed upward through the wire, which way would the magnetic force cause the wire to curve and why? Really quickly, before we talk about number 6, I want to go back to number 5. I need to make sure you really understand what's happening here conceptually. Okay, the first right-hand rule we talked about was right-hand rule number 1. Okay, that gives the direction of a magnetic force acting on a moving charge. This wire right here is not going to experience a magnetic field. Okay? There is a magnetic field around the wire, but it's one of its own creation. It's not going to experience a magnetic field, it's not going to experience a magnetic force created by its own magnetic field. Okay, so you could never use right-hand rule number 1 in this situation because there is no magnetic force, because the field that this wire creates cannot act on itself. So when you're looking at this picture right here, understand these X's that you're seeing, those obviously don't represent the magnetic field created by a current carrying wire, okay? Because we should have dots on one side if that was the case. This is a wire located in an external magnetic field. Okay, that's why it has the word external. That field has been created by some other means that we don't know. It's not explained in the problem. Okay, so make sure you understand, yes, current carrying wire does produce its own magnetic field. That is not what is happening in this particular situation, though. Okay, so here we have a current directed upward through the wire, which means we have positive charge moving up. The field, the outside external field here is obviously going into the page, and so if you point your finger straight and it's going straight up, your middle finger needs to be going out, and you need to rotate your hand and your wrist so your middle finger is pointing into the page. And if you do that correctly, your thumb should be pointing to the left, which means the magnetic force on the wire is going to be to the left. Okay, so that is question number 6. Okay, question number 7. It says a 48 microcoulomb charge having a velocity of 8.25 times 10 to the 6 meters per second enters an external magnetic field having a magnetic flux density. I don't know why they use that word, the IB. Magnetic flux density is the same thing as magnetic field strength. It's the same thing as magnetic field. Okay, that's B. 1.75 Tesla, that's B. Find the magnitude of the magnetic force. That is no problem at all. That is QVB sine theta. Find the magnitude of the force is nothing. I'll do it over here though. Okay, so Q is 48 times 10 to the negative 6. V is 8.25 times 10 to the 6. B is 1.75. And then if you look at the picture, you can see what theta is. Remember, theta is the angle between V, which is a vector, and B, which is another vector. Okay, so the velocity is clearly to the right. There's an arrow on the paper showing that. The field is going into the page. You can see that by the x's. So the angle between right and into the page is 90 degrees. And so that angle would be 90 degrees. Sine of 90 degrees is 1, by the way. And so all we really need to do for the magnitude of this calculation is stick this number into the calculator. Okay, so I'm doing 48 times 10 to the negative 6 times 8.25 times 10 to the 6 times 1.75. And I get 693 newtons. Okay, now the direction is a little trickier. So if you apply right hand rule number 1, you put your pointer finger to the right, your middle finger should be going into the page. That means the initial direction of this force is going to be up. And I say the initial direction of the force because, as I talked about in a past video, what's going to happen is the direction of the force is going to change, and actually it's going to cause the charge to move in a circular path like this, so it's actually going to curve. Okay, so that is question number 7. Okay, so pause it here before I erase. Question 8, it says a particle mass m and charge of magnitude q enters a region of uniform magnetic field B that is directed into the page. The particle follows a circular path of radius r. What are the sign of the charge of the particle and the speed of the particle? So first let's talk about the sign of the charge. We can clearly see that V is to the right, B is into the page, and so if you apply right hand rule number 1, you put your pointer finger to the right, you put your middle finger into the page. As soon as this particle enters the magnetic field, it should feel a force up. Now wait a minute. It bends downward. Why does it bend downward if it should be feeling a force up? Well, remember right hand rule number 1, that only gives you the correct direction for a positive charge. And so if it's doing the exact opposite of what we would expect, that must mean that this would be a negative charge that we're actually dealing with. Okay, so you can eliminate A and D. For the last bit of the question, you might be like, what the heck is going on here? But remember, we have circular motion happening here. Okay, centripetal force and all that stuff. Okay, here the centripetal force is provided by the magnetic force, which is QVB sine theta. But theta here is going to be 90 degrees, and sine of 90 degrees is 1, so I don't even need to write that. The question is asking about the speed. And so if you solve this for V, notice there's a V on both sides, so the V cancels out. Rearrange this equation to get V by itself, and you have Q times R times B divided by M. No square root or anything. Okay, so that means the answer must be B. Okay, so that is question number 8. Okay, so moving on. Question number 9, it says a beam of electrons. As soon as you see electrons, you should be thinking, okay, negative charge. I can use my left hand for this. Okay, if you have negative charge, either you can use your right hand for the right hand rule number 1 and just do the exact opposite, or you can just do your left hand. Either way is fine. Okay, so we have a beam of electrons that has a negative charge, moves between the poles of a magnet. In what direction will the electrons be deflected? Well, magnetic field always runs from north pole to south pole. Okay, so the magnetic field lines here would be going to the right. So if I'm actually going to use my right hand and just switch the direction. No, actually, I will use my left hand. That way I don't have to bend my wrist in a weird way. If you put your left hand out, keep your pointer finger straight. The electrons are going into the page. Your middle finger should be pointing to the right from north to south pole. Then your thumb should be going straight up. Okay, so the answer there is D. Okay, and by the way, just a hint on these questions, the magnetic force always has to be perpendicular to both the velocity and the magnetic field. So the answer to the question is always going to be perpendicular to the direction of the other two. So that means if you know that the field is going from North Pole to South Pole, that means that the force definitely cannot be in that direction. So you should be able to eliminate B and C just based off of that and narrow it down to A and D just because those two are both perpendicular to the two directions shown. Okay, question 10. It says the diagram shows three parallel wires, P, Q, and R, each having the same current I. The resultant force on wire Q due to wire P and wire R is what? Okay, so we're asked about the middle wire. Why is there a force on wire Q? Because wire Q is sitting in a magnetic field. To be more specific, it is sitting in the field created by both wire P and wire R. Yes, it's also sitting in its own magnetic field, but that doesn't affect itself. Okay, so we have to use right-hand rule number 2 to figure out the direction of the magnetic fields due to the other two wires. Now, if I use right-hand rule number 2 on wire R, I put my thumb going up in the direction of current. This is wire R. When I curl around, by the time I get to where Q is, my fingers are coming out of the page at that location. And actually, if you do the same right-hand rule for wire P, you put your thumb going down, because for wire P the current is going down. When you curl your fingers around that wire, when they get to the right side of wire P, they are also coming out of the page. And so both P and R create a magnetic field that at the location where wire Q is coming out of the page. Now I can switch back to right-hand rule number 1. I put my pointer finger going straight down. I put my middle finger sticking out, and then I rotate my wrist so my middle finger is coming out of the page. And then if you do that correctly, your thumb should be pointing to the left. Okay, so the answer there is D. Number 10. Okay, so I'm going to erase this. Question 11, two parallel wires are perpendicular to the page. The wires carry equal current in opposite direction. Point S is at the same distance from both wires. What is the direction of the magnetic field at point S? Okay, so let's see what this field would look like. So let's say this wire with the current coming out of the page. I use right-hand rule number 2. I put my thumb coming out of the page, and basically, if you do that, what it should tell you is that the magnetic field encircles this wire going counterclockwise, because your fingers curl counterclockwise. Alright, now, if you do the same type of thing for the other wire, you put your thumb into the page. If you were to draw the same type of circles, they would be going clockwise like this. Sorry, I can't draw better clockwise circles. Something like that. Okay, now, if you notice though, at point S, this field is kind of going up and to the right. And when we did it for the other current carrying wire, it was going up and to the left. And so what does that mean? That means basically that the X components of those magnetic fields cancel out, and the overall direction of the magnetic field at point S would be going up. In other words, let me erase this so you can see what I mean. The field due to this wire would be going up and to the right. The field due to the other wire would be going up and to the left at that one single point in space. And so the net effect would just be the x components would cancel out, and the field itself would be going up at that point. Okay, so that is question 11. Question 12. Horizontal wire PQ lies perpendicular to a uniform magnetic field. This is almost exactly the same as the calculation that we did before, only now we're told the direction of the force, and we're asked about the direction of the current. So we're told some values of stuff. We're given L is 0.25 meters. We're given B is 40 millitesla. We're given FB is 60 millinewtons, and we're asked about I. Now there's only two equations in this unit. Clearly this is the one with B, I, and L in it, because, you know, that should be obvious. Theta here is definitely going to be 90 degrees. I can see that just by looking, because the field here should be going from North Pole to South Pole. It should be going to the right, and it doesn't matter if it's going from P to Q or Q to P, it's still going to be at a 90 degree angle, right? You know, the angle between the current and the field is still going to be 90 degrees either way. Okay, so, and since sine of 90 is 0, or sine of 90 is 1, I don't even care about that. All I care is about the BIL. I is going to be 40 milli, sorry, not 40. You rearrange this equation, you get FB divided by B times L, so that would be 60 millinewtons divided by 40 millitesla times 0.25, and the only reason why I put the milli, I am plugging the units here, is because the two millis actually cancel each other out, and so don't matter at all. And so I just get 60 divided by 40 times 0.25 is 10, so that's going to be 6 amperes. Okay, so you can easily do that calculation without a calculator, which you would have to do on the IB exam because you don't have a calculator available to you on multiple choice questions. So the current would be 6 amperes. Now the direction, here we have to use right hand rule number 1 kind of backwards. Okay, so we know the field is going to the right, and we know the direction of the force is down because it says that in the problem. Alright, so we basically need to figure out, okay, if my middle finger is going to the right and I want my thumb to be going down, which way would my pointer finger have to be going? And if you kind of bend your right hand correctly, you should see that your pointer finger actually has to go into the page from Q to P, so the answer should be B for number 12. Okay, question 13. We had this as a warm-up question. The answer is A because it's the particles traveling parallel to the magnetic field, so magnetic force is automatically 0. 14, this is really similar to the type of question that we just did. We haven't really talked too much about the circuits unit yet, but here if you look, it's connected to a battery, and the long end is a positive side, and the negative side, the short end is the negative side, and the current is always going to come out of the positive end and go back into the negative end. And so I guess you do need to know that to be able to answer this question. So basically the current is going like this around this wire. The magnetic field lines are looping from north to south. Something like this. It's really horrible to try to draw this, actually. Okay, so my issue with this question is it's not drawn very well, to be perfectly honest, because I can't tell. I can't get a full idea of the three-dimensional picture here because of the way it's being drawn. And I know what the answer key says the answer should be, and I'm not exactly sure where they're getting this answer from. And so I am just going to punt on this question and just say that you will definitely not see that question again. Yeah. I understand how you would approach it in general, it's just that the picture's kind of drawn in a weird way. So let's go on to 15. A wire carrying a current I is at right angles to a uniform magnetic field of strength B. A magnetic force F is exerted on the wire. Which force acts when the same wire is placed at right angles to a uniform magnetic field of strength 2B when the current is I over 4? So we've seen questions like this before. This is just like one of those math questions where it's like, if this thing changes, how does this other thing change? And in both situations, the angle is 90 degrees, so sine 90 is 1, so we don't even care about that. So if the original force is, BIL, it's basically asking what is the new force if we take the same wire, so the same length, but now we double B, so instead of B we have 2B, and then we make I over 4. Okay, and so doubling B doubles the force, decreasing the current decreases the force by a factor of 4, and so we get BIL over 2, which is half of the original force. If you compare these two equations, right? Compare that to that, this result is half as much. So the answer would be F over 2, which is B. Okay, question 16. 3 parallel wires, X, Y, and Z carry equal currents. The currents in X and Z are directed into the page. The current in Y is directed out of the page. Which arrow shows the direction of the magnetic force experienced by wire Z? Okay, so now this is interesting. This is slightly different take on the question we did earlier. So wire Z feels a magnetic force because of the other two wires. But because all the currents are equal and distance is also a factor, wire Z is really sitting in the field created by wire Y. I mean, yes, it's also affected by wire X to some extent, but because the distance between Y and Z is less than the distance between X and Z, wire X doesn't really play too much of a role in this problem. Okay, I would suspect just by kind of looking at the problem that the field at Z due to X and Y would be in opposite directions, but wire Y is going to win because the distance is closer. So what is the direction of the field at wire Z due to wire Y? If you use right-hand rule number 2, you put your thumb out of the page because the dot represents out of the page. That field would look something like this, and it would be going clockwise. Okay, so at position C, notice that field would be going straight up. Okay, we're asked about the direction of the force on wire Z, so now we switch back to right-hand rule number 1. We put our pointer finger into the page, we put our middle finger up, and now our thumb represents the direction of the force, which should be to the right. Okay, so the answer to 16 is A. Okay, and then just a couple more questions. Question 17, we're asked to draw the magnetic field pattern due to the current. This is just a right-hand rule number 2 problem. Current is clearly going counterclockwise, like so. Okay, so you would just draw concentric circles centered on the wire with the direction counterclockwise. Okay, much better than I drew it here. Again, you would just draw like loops around the wire, centered on the wire, with the direction indicated as counterclockwise. Okay, 14b, we're asked to identify with an arrow the direction of electron flow in the wire. We're given the direction of the force and the field, but if they're talking about electron flow, remember electrons have a negative charge. So here we're actually given the direction of the force, so I'm using my left hand because I know electrons have a negative charge. I put my thumb of my left hand going up. I want my middle finger coming out of the page towards me, because that's what the field is doing. It's coming out of the page. And now my pointer finger, which represents the direction of the moving charge, is going to the right. And so I would indicate with an arrow to the right the direction of electron flow. Okay, so that is 17b. Okay, we're told that the horizontal component of the magnetic field of the Earth at the position of the wire is 40 microtesla. The mass per unit length of the wire is 1.41 times 10 to the negative 4 kilograms. It says per square meter. I don't know why it's per square meter, though. I think that's a mistake. It should be per meter. Because mass per unit length, mass over length would be kilograms over meters, not kilograms over meters squared. We're also told that the net force in the wire is 0. Determine the current in the wire. Okay, so you might be asking, what the heck does that mean? Mass per unit length. What is that? Okay, before you freak out too much, let's just start with this tidbit right here. The net force is 0. Okay, that makes me think Newton's second law. F net equals ma. I'm told the net force is 0, and I have two competing forces. Okay, I have magnetic force and I have gravity. Okay, now FB is given by BIL sine theta. Okay, so I'm plugging that in for FB, and mg is equal to the mass times the acceleration due to gravity, which on a free response question I should be using negative 9.81 meters per second squared. Okay, now clearly the direction of the current and the field is 90 degrees. I said that before, so I don't really need that. You might be asking, how do I know to use that equation? Well, they're asking me for the current. There's only one equation that has current in this unit, so that's not, that confusing. But I don't have the length, so let's see. I do have B, okay? I'm looking for I, so I is unknown, B is given. I don't have the mass of the wire, and I don't have L, but I'm given the mass per unit length. Okay, so if you're wondering what the heck is mass per unit length, I'm just going to give this a symbol. Let's call it X. What does mass per unit length mean? It's exactly what it sounds like. It is mass per unit length, which I will call X just to call it something, is basically mass over length. That's it. Okay, it's kind of like one-dimensional density, if you want to think of it like that. Like normal density is mass over volume. Mass per unit length is like, mass over length. In other words, the mass of this wire, by definition, would be X times L. Okay, now the reason that helps me is because I don't know the mass. I do know X. I don't know L, but watch what happens if I make this substitution into this equation. I get B. Actually, let me just plug in the value for B. B is 40 microtesla, so 40 times 10 to the negative 6, times I, which is my unknown, times L, plus XL times negative 9.81 equals 0. Okay, and you might be saying, well, that still doesn't really help you because you don't have the length. But watch what I can do now. And if this seems kind of convoluted, I apologize, but it is what it is. It's an IB problem. That's why it's a 3-mark question. Watch what I can do. Because both of these have an L in them, okay, I can actually factor out the L. Okay, so I can actually say L times 40 times 10 to the negative 6 times I plus X times negative 9.81. All of that is equal to 0. And I can divide the L out. If I divide both sides by L, 0 divided by L is 0. L divided by L cancels. And so now I'm left with an equation that's actually very easy to solve for I. Because now I basically just have a basic algebra problem. So I have negative 9.81 times x, which I also have x. So 1.41 times 10 to the negative 4, and that's equal to 0. And so I is equal to 9.81 times 1.41 times 10 to the negative 4 divided by 40 times 10 to the negative 6. And if you do that correctly, I'm doing 9.81 times 1.41 times 10 to the negative 4 divided by 40 times 10 to the negative 6. I get I equals 34.6 amperes, and I'm done with that problem. Okay, so what did I need to know? I need to know the basics of the right-hand rule, but I also had to know Newton's second law. I need to understand that. And then I had to figure out on my own what mass per unit length is, because mass per unit length is not part of the IB curriculum. Okay, and so this question is testing you on whether or not you can roll with the punches and figure out these things on your own. Although it would have been better if they had given you the correct units, because mass per unit length is not kilogram per square meters per just meter. Okay, so that is 17b. Okay, and then the very last bit of the question, proton moves along a circular path, blah, 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 label with arrows on the diagram the magnetic force on the proton. I mean, object in circular motion always has to have a force towards the center of the circle, providing the centripetal force, so, I mean, there you go. It's got to be towards the center, because it's circular motion. Label with arrows on the velocity vector, v of the proton, that would be perpendicular to the force. Okay, so now the direction I need to think about carefully, because I know the force has to be going down and to the left here. So I'm using right-hand rule number 1. I put my my thumb down to the right, because I know the force has to be as I've drawn it here. And I know the field is going into the page. Okay, if you do that correctly, you should get your pointer finger going straight out this way. Okay, so this is the direction of V. Okay, so FB was really easy to figure out, just common sense centripetal force, because it's circular motion type of thing. Figuring out V was a little trickier, because you have to use right-hand rule number 1 and kind of like backwards. Okay, notice that FB and V are perpendicular to each other, as they have to be. Okay, so that's 18A and 18B. And then for 18C, we're basically asked to find, it says for this proton, determine in meters the radius of the circular path. So here I'm using the centripetal force equation. I'm plugging in QVB, the magnetic force, because that is providing the centripetal force. Before anyone asks what happened to the sine theta, in this situation it's always going to be 90 degrees because V and F are perpendicular to each other. Sorry, V and B are perpendicular to each other, my bad. Theta is the angle between V and B. Okay, and they're at a 90-degree angle here. Okay, so that's why I didn't include the sine theta in the equation. So here, one of the V's cancels out. We are looking for R, and so that is just a simple rearranging of the equation. The mass of the proton is in the data booklet. It's something like, I don't think it's 1.67, it's something slightly different, but it is in the data booklet. And everything else we are actually given in the problem. We're given V. In the problem we're also given B and Q. The charge of the proton is the elementary charge, so that's 1.6 times 10 to the negative 19 coulomb. And then B is 0.042 Tesla. Okay, and so let's see what that would be. 1.67 times 10 to the negative 27 times 2.16 times 10 to the 6 divided by 1.69 times 10 to the negative 19, and then divide by 0.042, and I get the radius is 0.54 meters. It does say an appropriate number of significant figures. That would actually be 2 sig figs, because if you look at everything we're calculating, B has 2 sig figs, and you always keep the smallest number of sig figs in the problem. The IB will never take off points for sig figs unless it says in the problem to give your answer to an appropriate number of significant figures. If it says that, then one of the points is definitely for sig figs. Okay, so you always keep the smallest number of sig figs that you have available in the question, which in this case is 2, because 0.042 has 2 sig figs. Okay, so that is it for this worksheet. Hopefully you find that helpful. Please let me know if you have any questions. Please feel free to reach out to me by email if you have any other questions about this video.